quick survey. You can close your eyes if it makes it easier. You can close your eyes and raise your hand if the homework was easy for you. Okay? Close your eyes and raise your hand if the homework was not easy, but it was definitely manageable. Okay, and you can close your eyes and raise your hand if the homework was not manageable. It was too much. Okay, so did you guys get a look at that also?
Yeah. I closed my eyes.
That wasn't the point, Barnabas. So we've actually set up a more formal feedback system than this one we just did. Adana set up a feedback system through Blackboard where you can basically just fill out a few questions about how you found the homework in each particular lecture. So we'll be able to get more precise information about how you guys feel. Make sure to use that. That's why it's there. So if it doesn't get used, then we can't tell how hard the homeworks are, whether we're missing things in lecture that you would find interesting, or how the office hours are going, etc. So take advantage of that. Other announcements. Your project proposals are due on Thursday. So make sure that you're thinking about that. This homework has been assigned, the next one, and I have the feeling a lot of people didn't start this last homework one until a couple days before it was due. So I'd suggest starting it earlier than that this time, in general. Do you have another announcement?
Also a reminder that there is a form on the website where you can, if you haven't found a partner for the project yet, you can put your interest there and see what other people have been working on and find a partner for that.
Thank you. Yeah, so check that out. It's on the website. People have questions about anything before we begin? Okay, so today we're going to try to wrap up the lecture on first-order methods. We had 4 lectures on first-order methods, or actually 3 plus a lecture on subgradients. So I'm going to try to wrap that up, and then Barnabas is going to take over and talk to us about our first second-order method we're going to learn, and really kind of the prime example of a second-order method, which is Newton's method. So what did we learn? Last time we learned about generalized gradient descent. So this was the setting that we had a function f that decomposed as g plus h, where g was differentiable and convex, and h was convex but not necessarily differentiable. And we motivated this algorithm called generalized gradient descent by looking at what we did for gradient descent and applying the same quadratic expansion idea, but only to the smooth part, so only to g, and leaving h alone when we kind of make this expansion at every iteration. So in doing so, we got this algorithm called generalized gradient descent. And it used this thing called the prox function up here. So when we apply generalized gradient descent, we assume we know this prox function. It's called the proximal operator also. So given h and a real number t, the prox operator, when you pass it x, it returns to you the point z that minimizes 1 over 2t times x minus z squared plus h of z. Okay, so it returns to a point z. So let's just back up a second. We didn't talk about this last time. Is this uniquely defined, this operator? Is there only one such c that minimizes that? Does that answer depend on h, first of all? Okay. So h is convex, right? We know that for a fact. This is convex, this term. 1 over 2t times the norm of x minus z squared. In fact, this is not only convex, but it's strictly convex. It's also strongly convex, too. So if I have a strictly convex function plus a convex function, the whole thing is actually strictly convex. Right? Because if I forget the exact forms, but let's suppose I have f1 plus f2, and f1 is strictly convex, then if I evaluate this function at alpha x plus 1 minus alpha x, that's like evaluating these two at that point and adding them together. Here I get strict inequality, and here I get non-strict inequality. But overall, when I add them together, I still get strict inequality. right? When I'm looking at alpha x plus 1 minus alpha x, f of that, that's f1 of that same block plus f2 of that same block. And I get strict inequality here from strict convexity and less than or equal to here. So when I add them together, I still get strict inequality. So f is still strictly convex. So let's go over and look at that here. This whole thing is strictly convex. So what do we know about strictly convex functions? If we minimize them, they have a unique minimizer. Okay, and actually, I think that was something we might have covered too quickly or something, because I asked that question a couple lectures ago and people didn't know the answer. So it's on the mastery set for this week. So you're going to actually prove that and a bunch of other kind of fundamental things about convex minimization problems. So in other words, z is uniquely determined here. This is really a function. We pass it x, and it gives us back a unique answer. That's true independent of h, as long as h is convex. So here's the algorithm, just like gradient descent, except for we wrap it in this prox call. So we take a step in the direction of the negative gradient of g. G was the smooth part. And then we apply the proximal operator of h. And sometimes we write this whole expression as x minus t times the generalized gradient, where the generalized gradient is just defined so that this looks like the form of the update we're familiar with. Right? So if we just thought the generalized gradient be x minus the prox over t, then you can check that this is another way of writing the update. Questions about generalized gradient descent? Okay, so this algorithm is actually a very powerful tool to have, especially, or really only when you know the proximal operator. And we're going to talk about a few cases in which we do know the proximal operator. Yeah?
So this idea of proximal gradient also works with projected gradient, or?
Yeah, it's a great insight. It does, and we'll talk about that in a second. So just to reiterate what was said last time, this prox function doesn't depend on g, right? It just depends on h, and we just evaluate it at a particular point that depends on g, at x, at the k minus first iterate minus tk times the gradient at that iterate. That's just a constant at any iteration. We evaluate the proximal operator at that constant. So that's the only dependence on g of these steps, is evaluating the gradient. So if I told you that I knew the proximal operator for h, you could give me any g, and the algorithm would be just as hard as long as I can compute gradients of g. So it's not any harder to implement if I change g from being one function to another, as long as I know what the gradient of g is. And the convergence analysis that we talk about is going to be in terms of the number of iterations this algorithm takes to converge. But each iteration applies one proximal operation. And depending on h, that can be expensive or cheap. So we'll see an example of both. One where it's quite cheap and one where it's quite expensive. So here's the first example we looked at. We went through this in detail last time, so I won't do it again. But we're looking at the lasso problem. So it's like doing sparse least squares. G here is the least squares loss. And h is lambda times the L1 penalty. And the first thing we found out was that the proximal operator of this particular function h was just soft thresholding. So we take every component of the argument we're given, and we check whether it's bigger than lambda t, whether it's smaller than minus lambda t, or whether it's in between the two of those. And we just do a very simple operation in each one of those cases. If it's bigger than lambda t, we subtract off lambda t. If it's smaller than minus lambda t, we add lambda t. Otherwise, we set it equal to 0. So that was our first proximal operator. How do we prove that? Well, actually, we had proved from the subgradient lecture that that was the solution to this problem, just by looking at the subgradients and showing that the subgradient was 0 at the solution. So the algorithm now just evaluates the gradient repeatedly, x minus t times the gradient of g. The gradient of g was minus x times y minus x beta, because g was this least squares loss here. So x minus the gradient, t times the gradient, is just I'm guessing I'm using x verbally for the optimization variable here, but in the slides it's beta. So it's beta plus t times the gradient. And then we just apply soft thresholding to that over and over again. So as we let this run until convergence, this will give us a solution to that lasso problem. So that's nice. Now what happens if I changed, let's suppose I changed the least squares loss to a logistic regression loss. So instead of being in a linear regression setting, I'm in a logistic regression setting. So just think of that as some other function here of beta. And I still want to do sparse logistic regression. So I still have parameters beta, and I still want to set them equal to 0 or not. What would change in this algorithm then? Just the g, right. So all I would do is I would change this, instead of being the gradient of the least squares loss, to being the gradient of the logistic regression loss. So that would change very little in terms of the implementation of the algorithm. It'd be like one line of code you'd change. And if in general, if I just told you I wanted to do, say, a sparse generalized linear model, as long as you knew the gradient of the loss function, you could fit that no problem with this algorithm. So here is a comparison between the only two ways to know how to solve this problem so far, which are subgradient method and generalized gradient descent. We can't apply gradient descent because this part here is not differentiable, that L1 norm part, right? Because at the origin it's not differentiable. So here's just a comparison of, as I let the number of iterations vary from 1 to 1,000, and I'm looking at the value of the criterion at the kth iteration minus the minimum. And you can see that generalized gradient descent converges a lot faster than subgradient method, and in fact the y-axis here is on a log scale. Right? So it means that it's converging a lot faster than subgradient method. So if we wanted, say, to be within 0.01 of the optimal criterion value, we would take, it looks like maybe, well, I guess almost 1,000 iterations here of generalized gradient descent. But after 1,000 iterations, we know we're close to that level of accuracy with subgradient method. Question?
Can you actually comment on why that is? Like, what is subgradient descent, generalized gradient doing so much smarter?
Yeah, that's a good question. So Ada asked, what's the difference between subgradient method and generalized gradient in this case? So subgradient method, actually let's even back up and let's think about, we had subgradient method, which just looked at, already in terms of beta, since that's our optimization variable here, it let beta plus be equal to what it was before, minus t times g, where g was a subgradient of our function at the guess beta. And its convergence rate was 1 over root k. So that's how this, that's the form of this, the value of this difference as k changes. In terms of its order of complexity, it decreases like 1 over root k. And then we had this, this lower bound, which told us that actually any non-smooth first order method, i.e. a method that takes beta k to be in where we started, plus the span of the subgradients we visited so far. So if I look at any method that makes updates like this, it chooses an initial point and it evaluates subgradients, and it just updates the current guess into be the span of where we've been plus the initial point, then it can't do better than one over root k in terms of the convergence. So subgradient method is definitely one of these methods. At every iteration, it just puts it in, it takes where we've been, and then it just moves in the direction of the negative subgradient that iteration. So by induction, for example, you could argue that it always has this property. So why are we able to do, which we'll see in a second, I mean, we saw it last time, generalized gradient descent achieves a convergence rate of 1 over k for this problem. So is that contradicting this? Is that breaking this lower bound? No, it's not. It would only break this lower bound if generalized gradient satisfied this. Right? But it doesn't. Actually, it doesn't only look at subgradients of h. It performs a full minimization at every step of a squared error term plus h. So it uses a lot more information than just the subgradient of our current iterate at h. It actually performs like a partial minimization of our function. It minimizes over h completely when we replace g by a squared error loss. So it's able to do so much better because it's able to leverage a lot more information than subgradient method. All subgradient method can use is just, subgradients of our criterion at every iteration. Subgradients of g plus subgradients of h. It's a very general prescription, so we can do it for almost any problem. In particular problems, if we can do more than that and actually partially minimize by minimizing out over h when we replace g with a squared error loss, then we're outside of that kind of class of minimization algorithms. But we're able to converge a lot faster because we're leveraging more information about the problem. Just looking at subgradients is like a reduction of information. Does that make sense? That was a good question. And one useful exercise is that you guys should derive the subgradient method for this problem. You have the tools to do it, so just write out the steps and compare the steps to these steps. It'll give you a more kind of more concrete comparison between the two methods in this case. So here's the convergence analysis. We're not going to go through it. On homework 2, this was question 4, I believe, was for you to prove this. And the steps are laid out in the homework as they are here in the slides too. But we make the same assumptions as gradient descent, but we only make those assumptions about g, the smooth part. If the gradient is Lipschitz with constant L, which say at this point we know, and h is convex and we know its proximal operator in closed form, or we can evaluate its proximal operator, then we get the same convergence guarantees with gradient descent as we do with generalized gradient descent as we do with gradient descent. So it has the convergence rate of 1 over k. Just the one thing to keep in mind is that this counts the number of iterations that the algorithm takes to converge, not the number of operations. So the proximal operator itself could be very expensive. And we'll see that, like I said, in a second. This was our example of a cheap proximal operator, the soft thresholding one. Yep.
So can we compute this lambda for general LP norm or just for L1 analysis?
The proximal operator, you mean?
Yeah,
Because S lambda is just the soft thresholding. Yeah.
I need the proximal operator.
It's a good question. So the L2 norm is easy. The L infinity norm is easy. But anything else than that is not so easy. So it's certainly very hard for LP for p between 1 and 2. If I look at just a non-integral p between those two values. I think besides that, I'm not sure what else would be interesting. I'm not sure why you'd want to look at it beyond that, besides the infinity norm. But I don't think it's easy. That's a good question. Yeah, so you always have to go through the exercise of, can I compute the proximal operator? So I'm not going to go through the convergence analysis, but just keep in mind if you end up not doing the homework and you want to get a flavor, not doing that question on the homework, and getting a flavor of how it works, it's like our gradient descent proof, but I replaced the gradient with this generalized gradient. So everywhere where you saw the gradient of f in the original proof, now we see capital G, which is the generalized gradient of that function. And then there's a little bit of differences, but besides that, it's really the same. And we get the same conclusion for backtracking, that we get the same convergence guarantee, except for generalized gradient descent, there's not just one way to do backtracking. So that's one of the differences, is that there are several ways to do backtracking, and it's unclear which is preferred, but this is at least one that has a convergence guarantee. Okay, so it looks different than backtracking in gradient descent. What does backtracking in gradient descent look like? So backtracking for just gradient descent, we looked at f of our proposed update, x minus t, the gradient of f of x. And we quit if this was smaller than or equal to f of x minus lambda times t times the norm of f of x squared. Okay, in a lot of cases, we can just think of alpha to be a half. It's a parameter, but we can take it to be a half. It'll match what it looks like here. Or I can just rephrase that to be saying that we start with some large value, and while this is true, while it's bigger than this, we update t to be beta times t. So we shrink t. So take a look at the generalized gradient descent rule. You'll see that it actually looks at the value of g, which is just the smooth part, and not f. So instead of looking at f of x minus t times the update, it just looks at g. And it quits when this is less than or equal to g minus the inner product of g times the generalized gradient plus t over 2 times the generalized gradient squared. So what happens when h is 0? Let's just do a sanity check. We should get gradient descent as a generalized gradient descent algorithm, right? Because that's what we said last time. When h is 0, the proximal operator is really just the identity map, so we get 0. We get gradient descent out of it. So when h is 0, this is the same thing as f. F is g plus h. The generalized gradient ends up being the gradient of f, or the gradient of g. It's the same thing. So I get minus t times the gradient of g squared plus 2 over t times the gradient of g squared. So I get minus t over 2 times the gradient of g squared. And that's the same thing as just what we do in gradient descent. So this is the same thing as the backtracking rule for gradient descent when h is 0. When h is not 0, it gives us a different rule. And if you take a look back at the proof of generalized gradient descent, you can see where this is motivated. There's a particular line we need to hold, and we just basically say we're going to choose the backtracking exit criterion to satisfy that. So with that choice, we get the same convergence rate. So here's an example that we're going to go through in some amount of detail. That's a highly non-trivial problem that we can solve with generalized gradient descent that has a pretty expensive proximal operator. So the setting is matrix completion. So let's suppose we have a matrix that's m rows by n columns, and we only observe some of its entries. So this is motivated by, one of the real kind of important problems that motivated research in this field was the Netflix prize, where we think of the number of rows as, say, a bunch of users that Netflix has, and the columns as indicating a bunch of movies that each of those people may have seen. And since not everybody has seen every movie and rated every movie, we only have parts of that matrix filled out. Right? So for only some combinations of users and movies do we have a rating. And we want to, say, fill in the missing entries. We want to estimate the unobserved ratings of, say, people's preferences had they seen a movie that we haven't shown them yet. So this is the problem we solve in order to do that. It's one way of doing this. There are several ways. But this is a very kind of natural way to do it from the perspective of convex optimization. We look at all the pairs of, or all the entries of y that we have observed, and they have an optimization variable b. And we choose b to minimize the sum of squared distances on the observed step, plus lambda times, this is the nuclear norm, also called the trace norm of b. So number yij is our observed entries. and we choose B to minimize this criterion. So B, the nuclear norm of B is the sum of the singular values of B. That's how we define it. So if B has rank R, I sum its singular values from 1 to R. So the way that we think about this intuitively is that this is like a convex surrogate for the rank of B. So why is it convex? Well, if you attended Aditya's recitation a few weeks ago, I think he might have talked about that. It's also a norm. We know that all norms are convex. And so why is it a convex surrogate for the rank of B? Well, let's suppose the singular values were just 1 or 0. Then actually would be the rank of B exactly, right? We can always write B as, say, U times sigma times V transpose, it's SVD, where sigma is diagonal with entries sigma 1 down to sigma R, and then zeros below where it's after the rth diagonal element, where R is the rank. So if these happen to be just 1s or 0s, then its nuclear norm is its rank. The sum of these singular values is its rank. If they're not, then they play kind of the same role with respect to the rank as the L1 norm does with respect to a measure of cardinality. So the relationship is like B star is to rank of B as the 1 norm is to the L0 norm of B. Okay, so this is like the number of non-zeros in beta. So put kind of differently, this is like the analogy of solving a lasso problem, but in the matrix world. We're regularizing our solution towards one of low rank. Okay. So how do we do this? How do we solve this problem with generalized gradient descent? Well, we have to find its proximal operator and its gradient. Those are the two ingredients. So the first thing we'll do is we'll just rewrite this problem as the loss being a matrix times, or just I guess a linear operator of y minus the linear operator of b for Venus norm squared plus lambda times the nuclear norm of b. So I just defined this operator p omega to give me, if I pass it a matrix, say b, it's just going to give me the entries of b. So turn me back a matrix whose entries are the same as the entries of b if I and j happen to be in the set of observed entries. Otherwise, it gives me 0. So look, I'm just evaluating the entry-wise difference between two matrices squared, and this operator zeroes them out on the unobserved set. So that just gives me exactly this this sum here, which is only over entries in the observed set. Just a little more succinct way of writing it. So one thing you can check is that the gradient of this loss function, and probably the easiest way to check this at this point is just to think about this whole thing entry-wise. Right, this is a matrix, is just the difference between py and p beta, or pb. That's the negative difference. Again, it's probably easiest to check that entry-wise. Think about the derivative of every, with respect to bij for all ij of this criterion, and you'll see that it's the ith jth element of that. So that's one thing we figured out. And the next thing we need to know is the prox function. So the prox function here is we need to figure out which matrix Z minimizes this criterion. 1 over 2 times, so let's say this is prox of B minus C squared plus lambda times T times the nuclear norm of Z. So here actually there usually is a T here. I've just multiplied through by T so that the T is multiplying lambda there. So if we knew how to do this, then we just would repeatedly evaluate B plus or B minus T times the gradient through the prox function, and that would be our algorithm. So for lack of time, and also because part of this is on your homework for next week, I'm not going to go through this in as much detail as I wanted to. Maybe the TA and recitation can go through this week. But the way of finding the prox function, just like we did for soft thresholding, it involves computing subgradients of that h part. For the soft thresholding function, that h part was the L1 norm. We knew what its subgradients were. They just were like the sign if the component was non-zero, and otherwise it's between -1 and 1. Here, we have to know what subgradients of the nuclear norm are. And if we know what they are, then we can kind of prove that the prox function has a certain form. On your homework, you are going to show us basically this fact, that the subgradients of the nuclear norm look like a certain form. And after you find that out, you can prove that the prox function in this case is just what we're going to call matrix soft thresholding, to point out the analogy to soft thresholding in the vector case, except don't be deceived by this kind of common terminology. It's actually a lot more difficult to do computationally than soft thresholding is to do in the vector case. So what does this mean? So let's suppose B is U sigma V transpose. This is the singular value decomposition of B, SVD of B. Then what we can show is that the prox function here is just given by matrix soft thresholding, where this returns us a matrix. What did I call it? I guess we'll call this matrix U sigma sub lambda T V transpose, where we take the diagonal elements of sigma and we threshold them to 0 or not, or soft threshold them by the amount lambda times T. So we look at sigma II and we subtract off lambda T from it, and if that's smaller than 0, we just keep it at 0. Otherwise, we subtract off the amount lambda T. So it's the matrix U times the special sigma times V transpose, where U and V were the left and right singular vectors of B. And this special matrix sigma sub lambda T is a soft thresholded version of the singular values of B. So we just soft threshold every singular value by the amount lambda T. Why is this so much harder? It's because it looks like it requires computing an SVD. In order to apply the proximal operator, we need to compute the SVD of B, which is way, way harder than just soft thresholding a vector. Okay, so just to wrap it up, the generalized gradient steps look like this. We have a guess B at some iteration. We add to it, or we subtract off T times the gradient. The gradient was actually minus Py minus Pb, so subtracting off the gradient is like doing plus T times that. And we take this whole thing and we soft threshold it, this matrix, by an amount lambda T. So at every iteration I have to compute the singular value decomposition of this whole guy, then I have to soft threshold at singular values, and then put it back together, and that becomes B+. So that's way more expensive than just what it was for the lasso case. So this is the generalized gradient descent algorithm for matrix completion. There's one special case that has a special name. If we take t equals 1, then we get a simplified form of this. And we know actually that this will give a convergent algorithm. Because in this case, the gradient of g is 1 Lipschitz, which means that it's Lipschitz with constant L equals 1. So t equals 1 over L will converge, or t equals 1 will converge. So that you can check just from what the form of g is. So in that case, when t is 1, what do I get? I get soft thresholding of b plus 1 times the projection of y, or the p of y. And then I get plus b minus its projection onto the observed set. B minus p of b. And I can think about this as just p of y plus, how did I write in the slides? P perp. I'll write it a little differently in the notes. P of lambda complement of b. Right, so this is going to be returning for us now 0 if the element is in the observed set, and the element of b or negative the element of b if it's in the unobserved set. So it's like applying the same operator but to the complement of the observed set. So look at every step. We take the observed entries of our matrix, and we fill the rest of the entries of that matrix that are unobserved with our guesses at what they were from that iteration b. That gives us one matrix that we form together, right? Observed from y, unobserved from our guess. We take its SVD. You look at the singular values, not singular value composition. We soft threshold them by an amount lambda t, and then we put it back together. So it's like a rank reducing step. And that gives us our guess of the current iteration. Good question. Yeah. Thank you. So this is called soft impute. That's the name of this algorithm. It's really just generalized gradient descent with t is 1. But from what we know about gradient descent, generalized gradient descent, this will converge at a certain rate. So it's a pretty simple and effective method for matrix completion. Okay. So this goes to answer one of the questions that was asked earlier. Why do we call it generalized gradient descent? Well, there's several special cases of generalized gradient descent that give us algorithms that we already know, or maybe that we don't already know. And that's why it's referred to usually as generalized gradient descent. So when we take h to be 0, we get gradient descent. So it's like a generalization of gradient descent. When we take h to be the indicator function of a convex set, we get projected gradient descent. So why is that? It's because the proximal operator for any value t of a point x, in this case, is 1 over 2t times x minus z squared. It's the argmin of all this stuff over z plus the indicator function of a convex set. Right, so this is infinity if we're in the set, and it's 0 if we're not. So another way of writing this, it's the argmin over only points z and c of just x minus c squared. or z in norm. It does, the t doesn't matter, the 2 doesn't matter, the square doesn't matter, right? Because at this point, they're all monotone functions of just this guy. So this is really just the projection. It's the exact thing as the projection onto the set C of x. So at every step, we're projecting onto the set C, which is just projected gradient descent. So that's nice, because it means that we can do gradient descent with constraints as long as we can project. And we've already proved that it converges. And we already have a recipe for doing backtracking. And we already know what the step sizes should be if we want to take them to be fixed, etc. And when g is 0, we get this special thing called proximal minimization, which, as far as I can tell, is not really studied beyond a few cases, but it's also an algorithm in its own right. Okay. So we went through this already. This was projected gradient descent, and here's the picture. At every step, we just take a step in the direction of the gradient of g, of the negative gradient of g, and we project back onto the constraint set C. So it's like, if here was our picture, if we were trying to minimize over this constraint set, and these are the contours of g, then we'd try to move in the direction of the negative gradient of g, but we'd force ourselves to be back on the set at every iteration. I like the connection here between projected gradient descent and generalized gradient descent, because this is very non-obvious, at least if you just studied gradient descent, that you could kind of apply all the same rules to these updates, the projected updates. It seems like projecting should add a bunch of complication. But when we studied it from the perspective of generalized gradient descent, and now it tells us that it doesn't really. It's really this, they're all one unified algorithm from the perspective of that decomposability, g plus h. Okay, well, we're going to skip through proximal minimization. So just very quickly, if we can't evaluate the prox, then generally speaking, all bets are off. We can't really use proximal gradient descent. So you might think, well, let me treat that as another minimization problem, right? Because I know how to do optimization. So at every step now of generalized gradient descent, I'll start an optimization subroutine where I apply, say, subgradient method or something else to finding the prox function. That's not a bad idea. And it may work in practice. But theoretically, it's not very sound. We're not really assured that that's going to converge to the solution. And in practice, there are lots of examples where it doesn't work. So it's unclear at this point when you can exactly do that and when you can't. There are exceptions, and I linked a paper here that proves convergence rates for inexact proximal gradient minimization, where you can actually do that in a step, not exactly. But they're very specialized conditions. Basically, the errors you make as you inexactly solve this proximal minimization step have to be getting smaller and smaller at a very rapid rate. If you can assure that their errors are getting smaller and smaller, then you can still apply this inexact proximal gradient method. All right, so what we're going to do is we're going to skip acceleration. You're going to see acceleration on your homework. And you're going to just basically have to implement it. And hopefully from that, you'll appreciate its utility. And if we have time, we'll come back and we'll talk a little bit more detail about acceleration as a method. But acceleration is a tool that you apply to these first-order methods to accelerate convergence to the solution. You'll get to see on your homework, if you choose to do question 5, it in action, it accelerating matrix completion in this case on your homework. But because it's not, I'd say, as core of an idea, and because we're a little bit short on time, we're going to skip it for the time being. But we'll come back to it if we have sufficient interest and time in the future. All right, so let's take a break, and then Barnabas will resume with Newton's method when we get back.
So we are going to discuss Newton methods, and it's also a huge topic. So we could talk about this in the whole semester, but we are not going to do that, only today in the next, maybe, I don't know, 25 minutes. And Thursday, and then we are going to discuss some related topics on conjugate gradients and quasi-Newton methods. If you want to know more about these topics, I really recommend these books. Some of them are really very gentle and easy to read, so it can be lots of fun. So the goal for today is to define Newton method and see how to apply this to find the root of a nonlinear function and how to use Newton methods for unconstrained minimization problems. We will see how to motivate Newton methods using quadratic approximation, and then we will discuss the rate of Newton's methods, and I will talk a little bit about Newton fractals as well. And in the next lectures, we will discuss conjugate gradients and quasi-Newton methods. Okay, so Newton methods is originally developed for finding a root of a function, and it's also known as Newton-Raphson method. And this is a problem. So we have a phi function that maps real numbers to real numbers. We know that there's a x star where phi x star is 0, and we want to find x star, right? That's our problem. And let's see a little bit of the history of this. So what do you think who applied the Newton-Raphson method first? No? Probably it was the Babylonian people. So they wanted to find the square root of a number s. And they realized that, if x, you just have to solve this equation that x squared minus s is 0. And then they realized that if you do this iteration here, that xn plus 1 is 1/2 xn plus s over xn, then this will converge to the square root of s. And it turns out that this is a special case of the Newton method. So maybe that was the first application of Newton's method. And here you can see if we run this iteration from, say, 50, so let s be 100. And if we run this iteration from 50, then you can see that we converge to 10. If we run it from 1, you can see it indeed converges to 10 again. But say if we run it from -5, then it will converge to -s, -10. Okay, so if you run this Newton iteration from a negative number, you might not get to the true answer. Clear? Questions? Okay, so Babylonians were the first. Who was the second? It was Raphson, probably, who developed the Newton's method before, I think 9 years before Newton. Their goal was the same, finding roots, but we will discuss how to find roots of general nonlinear functions. They just discussed this for polynomials. And then Thomas Simpson was who really invented that Newton-Raphson method that we are going to discuss. And he showed how to solve nonlinear equations with this method and how to solve optimization problems. And then Cayley generalized this method to convex numbers as well and realized there are lots of difficulties there. Okay, so this is the history. Yes? Oh, I might be wrong then. So, yeah, I thought it was 60, but if I wrote 90, I have to check. So I just saw that he was before Newton. But I think the first publication, it was something like 1912 or something. So they invented this, but it was not published that time. Okay. So this is our problem. There's a phi nonlinear function. Phi x star is 0. We are looking for x star. And what we can do is that we do a first order Taylor linear approximation of our function phi. So now phi at the point, say, x plus delta x is, of course, phi x plus the first derivative of phi multiplied by delta x plus a little o term that we will just neglect. And if x plus delta x, that's x star, then, of course, phi of x star, that's 0. And therefore, we have 0 is approximately phi of x plus 5 prime x multiplied by delta x. And we solve this for delta x. We will have that delta x is just minus phi over 5 prime. And this is the this will lead to our iterations. That is, we will just set x k plus 1 to be xk minus phi over 5 prime. Oops, there's xk here and xk here. Questions? So the motivation is clear, right? Any questions? No? Good. So this is how with this iteration, we will find roots of nonlinear functions. So you can see that here, this is our function phi. We want to find this root here. And we start from a x naught, phi of x naught point here. We do a linear approximation. We check, this will be f hat. We check where f hat is 0. And in that point, we repeat this iteration. Right? So phi f hat is this linear function. We solve this equation where this linear function is 0, and then this will be our new point x, and this is the delta x, and t is the Newton step that we make. And we do this iteration, and hopefully it will converge to the root of the nonlinear function. Okay, so this is for this. Our goal is to find the root of this function, and you can see in each point we fit a linear approximation. We check where its root is, and we continue this iteration. And indeed, in this case, we converge to the root of this function. That's clear so far, right? Okay, this can be generalized to multivariate functions in a straightforward way. So we have a function f that maps n-dimensional real numbers to m-dimensional real numbers. Then we just do the generalized Taylor approximation in the same way as we did in the one-dimensional case. So 0m is just means it's an m-dimensional 0 vector. Okay, and in x star this is 0. So let's do a Taylor approximation in this x star point, which is just x plus delta x. This is the first order Taylor approximation. This is the first order, first derivative. Sometimes I use nabla operator, sometimes prime. And now you should notice that this is a matrix actually, right? Because delta x is an n-dimensional vector, and we map from the n-dimensional Euclidean space to the m-dimensional Euclidean space. Again, we neglect the little o term and solve this for delta x. And we will get this equation that 0 is just f of x plus the derivative of f of x plus delta x. We solve this for delta x, and we got basically the same equation that before, except that this inverse might not exist, but you can use the pseudo-inverse. Right, and you do the same iteration. So that's the general Newton iteration for this problem. And of course, we can discuss when it will converge to the root, when it won't converge to the root. Okay, so how should we use this Newton method for minimization? Ideas? So we know how to find the root of a nonlinear function. How will that help us to find the minimum of a nonlinear function? Yeah, so we will assume that the function is differentiable, and then we will try to find the root of its derivative. Right, so let's assume that f is a function that maps n-dimensional vectors, real vectors, to a real number, and we want to find the minimum of this function f. Okay, so we do the same thing, that our goal is to find the root of its derivative, and we write the Newton system for its derivative, and of course this will have this form here, that is the first derivative of f of x plus the second derivative of f of x multiplied by delta x, that should be 0. And we solve this for delta x, and that will lead to the iteration, that is k plus 1 is xk minus the second derivative of f, again in xk, inverse multiplied by the derivative of f at xk. Is it clear? Okay, so that's the Newton method. Very simple. So now you might wonder why I said that we can spend the whole semester just studying this. Okay, so you can do this iteration, and then a couple of things can happen. Either it converges, then you are happy, but actually it might diverge. You might get into loops as well, or it might converge to loops. So you are in a point, then you go to a second point, then you go to a back, but closer to some x not point, back again. So you can just converge to a loop, like I'm dancing here, right? So it can be quite messy, but we will see conditions under which this will converge to the right solution. Okay, so now we know Newton method, and what we are going to discuss is how good is this Newton method. The first observation is that if the second derivative is a positive definite matrix of f, then the Newton step, that direction, is a descent direction. So at least that step is pointing to a direction that's a descent direction. Does it mean that the Newton iteration will always decrease the function? So there's a direction, that's descent direction. And there's a vector that I'm going to do. So if that vector is too long, then I might get into troubles, right? Okay, so let's see the proof. So we know that if we just need to calculate the inner product between the Newton step direction and the gradient, right? And if that's negative, then it means that it's a descent direction. And that's easy. So we know the Newton step, delta x, is just minus the second derivative. Sometimes we call the inverse of the second derivative. Sometimes we call this Hessian matrix multiplied by the gradient. And let's see the inner product between the Newton step and the derivative. And it's very simple. It's just Newton step here. And this is the transpose of the derivative. And you can see that because we assumed that the second derivative of f is positive definite, this will be a negative number. So it's indeed the Newton step is a descent direction. Do this if I'm right. Good. Okay, so it's pretty simple so far. And here I just listed a couple of properties of Newton method. So we will see that under some conditions, the rate of the convergence will be quadratic, which is pretty good because it's faster than the gradient descent algorithms that Ryan talked about a lot. But there are some drawbacks. So for example, it can break down if the second derivative of xk is, so it's not invertible. And we need to invert that matrix. So we can have problems there. Or the Newton method, it can diverge if we start from a bad location or or the function is just not pretty enough that we want to minimize. It can be trapped in a loop, or it can converge to a loop as well. Okay, here is another motivation using quadratic approximation. So let f be a differentiable function, say twice differentiable function. So we use a second order Taylor approximation. So phi is a second order Taylor approximation of this function f. Phi at the point, and we do this Taylor approximation around xk. So now phi of x is f of xk plus the transpose of the gradient multiplied by x minus xk plus this expression where again this is the Hessian matrix at xk. Right? We know second order Taylor approximation. Okay. So let's assume again that the Hessian is positive definite. It implies that this phi function has a strict global minimum. Right? This approximation looks like this. And let's try to find the minimum of this approximation phi. This will be xk plus 1. Where is the minimum of this function phi? Where its minimum, where its derivative is 0. What's the derivative of this function phi? It's, well, just this expression, right? The gradient plus the Hessian multiplied by this vector. Okay, this is 0. We have to solve this for xk plus 1. And that's actually the Newton step that we already discussed. Right? Xk plus 1 is xk minus inverse of the Hessian multiplied by the gradient. Okay, and this is its explanation. So this is our original function f. At the point x, f of x, we approximate this with this quadratic function, that's f hat. We minimize this function f hat, and we move to that point. And in the second iteration, we again approximate this f with a second order function around this point, and hopefully at some point we will converge somewhere here, the minimum of f. Right? Okay, and of course, this quadratic approximation is good when we are close to the true minimum. But if we are far from it, it can be pretty bad. Okay, so let's discuss the convergence rate of the Newton method. First, we will discuss only a very special case where the function maps real numbers to real numbers. And we will have very simplified assumptions on the function f. So the results will be not quite general, but it will help your understanding, I hope. Before that, let's just review. You did this with Ryan, but let's just review what we know about rates, how the what it means: quadratic rate, linear rate, sublinear rate, superlinear rate. I hope you know that, but just to remind you. So we say that a sequence Si has a linear convergence rate if it's converging to a, say, S bar number. And for the limit of this expression, it holds. I denote this limit by delta. It holds that delta is less than 1. You remember this, right? Mm-hmm. OK, good. So that's linear rate. And an example, for example, if Si looks like this, that's C times Q to the I, where Q is between 0 and 1, then it will converge to 0 with a linear speed, because you can, again, calculate this expression, and you will see that its limit will be Q, which is less than 1. So that's the linear rate. What's the superlinear rate? So it sounds like something that's faster than this linear. So when can it be faster? If delta is 0, exactly. So an example is, for example, Si is C over I factorial. And if you calculate, again, this ratio here and in the limit, then the ratio will be just 1 over I plus 1. It will converge to 0. Sublinear, what's sublinear rate? It should be slower than the linear. Yeah, but what's the definition? With delta.
Limit is 1.
Yeah, exactly. When the limit is 1, that's the sublinear rate. And an example can be, for example, this C over I to the A. Again, if you calculate this ratio, then you can see that its limit will be 1 if A is a positive number. OK, and quadratic rate, what's the difference? Is that here we have 2, right? And we need that this limit should be finite. OK? So what we want to prove that for the Newton method, under some conditions, we can get this quadratic rate, which is much faster than the linear rate of the gradient descent algorithm. OK, so here is an example. So it's like double exponential speed if Q is between 0 and 1. Right? So Q to the 2 to the I, that would have quadratic rate convergence to 0. Yep.
We only need that finite, not less than 1, just finite.
Oh, for this, yeah, it's just have to be finite. Yes?
So when you say it's going to be faster than the linear rate of gradient descent,
Mm-hmm.
then you're talking about the linear rate that you get if the function is strongly convex, which is the
Yep.
exponential
Mhm.
that we talked about like 2 lectures ago or something.
Yep, yep.
Right? That's what you're comparing it to.
Yep.
Great.
Other questions? Good question. No. So this is clear. So let's see the proof. So our goal is just to find x star, where f of x star is 0. And let's assume that f has continuous second derivative in x star. Then I should stop soon. Then we can use the Taylor's theorem, which says that f at x star will have this form, right? That there's a psi n between x and x star, such that f of x star is has this value, right? We assume that gradient has inverse, so it's not 0. You multiply this equation with the inverse of this gradient. Then you will get this expression. And after some algebra, you can, next class we will repeat this. I'm just briefly describing the ideas. You can rewrite this expression to this one, nothing fancy. But what now you have to observe is that this expression here, this is, say, let this be epsilon, this is epsilon squared. And then what's in the other side? By the definition of the Newton step, this will be x star minus x n plus 1. That's epsilon n plus 1. And now what you can observe is that the error, the distance between x star and x n plus 1, so epsilon n plus 1 is this expression multiplied by epsilon n squared. So if this expression here is bounded, then epsilon n plus 1 will be a bounded term multiplied by epsilon n squared. That will lead to a quadratic convergence. We will come back to this next class, and then we will discuss the details. Okay? And now you can leave.